Now let's talk about the second part of this lecture, image enhancement. And as you can imagine, we will still use a lot of things we have studied on the other supervised learning tasks, especially the recognition task, to construct the basic learning models, to recognize the pattern and perform the task. But besides the modeling part, the challenge for image enhancement is generally how we can generate visually realistic images. And this is actually a very tricky part. How do we measure the visual realism? It's very tricky. It's very challenging. And the previous study has shown that simple measurement like L2 or L1 distance between pixels does not tell us whether the two pictures are visually similar. And there actually a solution based on convolutional network, that is to learn what is real. Let's see how we can make this work. The core idea and the technique behind this is generative adversarial networks. And in terms of computer vision task, it basically means two things. The first thing is to learn a convolutional network to generate the target images. The convolutional network can be fully convolutional network, which will map from one type of image to the other type of image, or it can be a pure upsampling network that can map from a random vector to a new image. And the second component is a discriminator to tell whether an image is real or not. And then at the learning time, we want to optimize the generator to fool the discriminator, and then optimize the discriminator to tell that the image generated is actually fake. And in the end, this is actually a two-player mini-max game. We can summarize the whole idea in this equation. The first part is how we learn the discriminator. So given a data point in the whole data distribution, which means they are the real data point, our real image. We want to optimize the log likelihood of this data point in the output of this discriminator. And here again, we are optimizing the log likelihood. And the other component is we want to minimize the probability of the generated image is determined as real by the discriminator. And of course, if we want to do a minimization, we can just do a inverse of the depth output. And then at the end, we want to maximize the discriminator so that it can both tell what is real and what is fake, and at the same time minimize in terms of the generator so that it can have a very low cost. It can have a very low loss determined by the discriminator so that the output of the generator is very similar to the real data. So that's basically why we call them adversarial networks. We have our discriminator and generator. They are fighting each other to optimize each other, and in the end, they both become better. And one of the important work using the generative adversarial network is called image-to-image translation. And the task here is very easy to understand. We have usually we have a input image. It shows the structure. For example, here it shows the structure of show a semantic segmentation, tell you that where the road is, and then the task is to generate a realistic image to synthesize based on the input structure. And you can imagine that this can be very useful for layout design. Say I want to have a car here, and then the network model will automatically synthesize a plausible picture based on my layout idea. And similar things can be true for the facade layout. So here we put the windows and put different levels on a planar graph, on a planar design, and then our network can automatically generate the output structure to tell you that what the real building may look like, and other examples like image colorization and also generate a real image from a boundary. So the generator, as you can imagine, is very similar to what we did for segmentation. In this case, we have input map, like it can be encoding of the segmentation or a boundary map, or it can be the black or white image. And then we want to generate another output on the target domain, like the synthesized image conforming to the layout or the colorful image. And we can use this encoder-decoder network to aggregate both spatial information and context information together. Here, this work actually extended the generative adversarial model into a conditional case. Instead of only have one input tell that whether the generated result is real or not, we also give another condition, like the original input of the generation network to the discriminator, and then the discriminator is supposed to compare between the original input and the generated result to see that whether the generated result is a good output from the original input, and that's why it's called conditional. And of course, this is the negative example for the discriminator, and the positive example for the discriminator would be the original image pair. So in the training data, we know that what is the full original image for this boundary map, and then we can use them to form the positive example for our discriminator. So of course, the formalization or the loss is also changed a little bit from the general GAN to the conditional GAN. And here, as I showed in the previous picture, this part, the discriminator takes two input. One is the input for the generator, and the other is the desired output. And then the discriminator should say that to learn what is the real data, what is the real output. And then, on the other hand, it will try to tell that what is fake. And it turns out that this conditional network is conditional adversarial network is very effective. Those are some results based on different inputs, and here there are. This is the segmentation map for outdoor scene driving data, and here is the segmentation for building facade. You can see here, if we only use L1 loss, that means that we do not use the adversarial network, and only have the compare the generated output with the desired output on a pixel basis. Then the output usually look blurred, and it doesn't look real, even though that the L1 loss can be really small. And on the other hand, if we only learn the discriminator or use the generative adversarial network, and without using the L1 loss, we also have something undesirable, even though the result looks much sharper and real. And the best results can be achieved when we combine these two laws together. And this is the true for a lot of other conditional generative tasks. For example, we want to have some input and want to do some touch up to generate the good output. And usually the L1 loss and GAN are both very important to achieve the goal. So this is very nice. Now we can have a generator and discriminator to translate image from one domain to another domain when we have a direct correspondence. But what if we do not have the exact target? Here is what may happen. So in the previous slides, we have been talking about paired image-to-image translation, which means that for each source image, at the training time, we have its targeting image exactly, and we can use this input and output to supervise our networks. However, in a lot of cases, we do not have this direct pair. we only have two domains. Say the first domain, the source domain, can be real photos, and the target domain can be the paintings from a particular artist. And our goal will be is to transfer from the real photo to a painting that in the artist's style. However, at the training time, we do not know exactly how we can paint this particular picture by this artist or in this style, because this artist may already passed away for 100 years. The idea to resolve this problem is called cycle consistency. So this is the general framework. We have image from two domains, and then instead of learning only a generator that map from one domain to like map a image or input from one domain to the other domain, we also learn a reverse mapping. It's basically the reverse of this generator, or here we just call it mapping to avoid confusion. We have this forward mapping and backward mapping to transfer between these two domains, and at the same time we have two discriminators to tell that whether this image belongs to this particular domain. And what the reason is called cycle consistency is every time we will for input we will map it input image to the to another domain or to another set using our first mapping function, and learn a discriminator to see that whether it's realistic in this particular domain. And at the same time, we will do a reverse mapping using the f, and then map it back to the original domain. And then we can say that when it's mapped back, it should look very like to the original image. And this is what we call the cycle consistency. And at the same time, we can also do the reverse way to jointly learn GF and DXDY. So that here, instead of learning one generator, one discriminator, we actually learn a pair of generator and a pair of discriminator, and then use the cycle consistency to calculate the loss, in addition to the discrimination loss. And here is some illustration of these two mapping. You can see this is a mapping from a real picture to a painting using the first mapping, and then we can reconstruct the photo based on the reverse mapping. And this is to map from horse to zebra and back to horse. And those you can see here. The goal is to do this cycle so that the reconstruction of or concatenation of G and F can map this generated image back to and compare it and make it similar to the original input. And it turns out that this technique is very effective in this type of unpaired image-to-image translation. And this is kind of the starting point for a lot of other methods. And here are some more results. Here we can map input image to the artworks of different artists. So this to show that this model actually can learn based on target set, can actually learn a diverse types of style transfer. And it can, for example, here is a Monet and also other artists. So they are all in very different styles, and they all look similar out of the to the other works of that particular artist. Here are some more examples to do category level transformation, and this is to transfer between horse and zebra. So you can see that the network can very vividly putting a strap on the horse to make them look like zebra. And at the same time, if the original image is a zebra, it can also work like the strap remover to transform the zebra back to the horse. And of course, this technique does not work on all different categories, and those pairs of categories usually share some similar properties. And how we can make this type of method even more generalizable and be usable for even broader set of categories is still under active study now. And this method also has some other type of failure case. For example, if the image is compositional, or which means that this image can have multiple elements, then the methods may not tell that what are the targeting objects in the particular image and try to transfer everything in the image to the target style. Like in this case, the model not only transfer the horse and put zebra stripes on it, but also put the stripes on the other objects like the person and also the background stones. It's worth mentioning that currently the generated images are looking more and more realistic, and especially in terms of in some simple domain like a human face. For example, let's take 5 minutes to pick out that which of those faces are actually fake. Okay, by now you may all have your own answers, and the real answer is they are all fake. If you like to play more with this, you can go to the website called "This Person Does Not Exist." So all those profile pictures are generated by models from some random seed, based on the technique we describe, like the segmentation, the fully convolutional network, and generative adversarial networks. And of course, to generate the image at large scale and work on a lot of person, there will be also a lot of other engineering works and other algorithm innovations. But overall, the state of art is so convincing that it's become even threatening for a lot of people, because it basically means that we can have pictures or video footage of events that have never happened. And in the past, we used to use those pictures, footages to prove what may happen. But now it's becoming more and more challenging to tell that what is real and what is fake. For example, I'm sure that we will all enjoy this video.
I appreciate the tenor of the conversations. I think it will actually yield results before the end of the year, and I look forward to continuing this dialogue in the months ahead. Thank you very much, everybody.
I like to conclude the lecture on supervised learning with super resolution. So the task is very simple, and you may need it a lot in your daily life. That is, if you are given a low resolution image, and we want to upsample the image so that we can fill in the details into the image and be able to see the picture more clearly. And this is actually becoming more and more important task because our screens are having higher and higher resolution, and we need it can show more and more details in the picture. And at the same time, if you can perform super resolution very well, then we only need to transmit the low resolution images. And the other application also include that you may have an old photo with low resolution and you want to upsample it so that you can see it more clearly. You actually have all the ingredients to solve this problem now. So I think you can even construct your own paper on super resolution. For example, if you want to get supervision, we can easily downsample any all the high resolution image in our photo gallery and learn how to upsample the image back. And if we, in terms of modeling, we have already introduced how we can get pixel level predictions and how to upsample with deconvolution. And the tricky part about super resolution may be higher requirement for spatial information, and it will require more details at pixel level, and therefore you may not be able to afford to downsample the feature map. At the same time, if you want to have large context, then you can use dilated convolution. And to measure that whether you generate image looks real or not, you can use GAN in addition to the other pixel level measurements. So I'm eager to know that what will be your recipe if you are going to solve this problem. And that concludes our lectures on using deep learning for the supervised learning tasks. So we can, in addition to the labels for recognition task, we can obtain supervision to bootstrap the models and even to train the models from simulation, temporal information, and some domain difference. And we can use convolutional networks to learn a very good pairs from large amount of data for the yield post problems like depth estimation. And for the low-level vision tasks like correspondence and style transfer, we can actually use a lot of the networks and models we designed for recognition tasks. And in addition, we can use GAN to learn what is real.